In this module, we will discuss potential energy surfaces and their importance in chemical kinetics. Previously, when discussing the Arrhenius equation, we introduced the concept of activation energy. It represents a barrier that must be overcome for a reaction to proceed. This energy barrier determines the rate constant and plays a crucial role in controlling the kinetics of a reaction. This figure illustrates the concept of activation energy. It shows the potential energy of a reactive system as the reaction progresses. The peak of this curve defines the activation energy, the energy barrier that must be overcome for the reaction to proceed. Now we will explore this concept in more detail. The potential energy of a system consisting of multiple atoms depends on their relative positions. In the case of a diatomic molecule, the potential energy can be described as a function of a single parameter, the interatomic distance r. You are likely familiar with potential energy curves that describe the variation of potential energy as a function of bond length in diatomic molecules. These curves provide insight into molecular properties such as the equilibrium bond length and dissociation energy. Since a diatomic system has only one degree of freedom, the bond distance between the two atoms, it is the simplest case for studying interatomic interactions. In a simplified model, we can represent a diatomic molecule as two spheres connected by a spring. This approximation follows the harmonic oscillator model, where the potential energy depends on the bond length and varies symmetrically around the equilibrium distance. However, a purely harmonic approximation is insufficient for many purposes, such as describing the breaking of molecular bonds. The Morse potential provides a more accurate description of molecular vibrations compared to the harmonic oscillator model. This figure shows a comparison between the potential energy as a function of bond length for the harmonic oscillator model and the Morse potential. The Morse potential explicitly accounts for bond breaking and includes the dissociation energy, the energy required to fully separate the atoms in a diatomic molecule. Additionally, it reflects the unharmonicity of real molecular bonds, the fact that energy levels become closer together as the bond stretches, in contrast to the evenly spaced levels of a harmonic oscillator. Despite these refinements, the Morse potential very well approximates harmonic behavior near the equilibrium bond length. For systems with more than two atoms, the concept of a potential energy curve extends to a potential energy surface, PES. While in a diatomic molecule, the potential energy depends only on a single variable, the bond length, additional degrees of freedom must be accounted for in systems with more than two atoms. Instead of a simple potential curve, we obtain a multivariable function that describes how the potential energy of the system depends on all possible atomic arrangements. The potential energy as a function of multiple variables, such as bond lengths and angles, can be represented as a surface or hypersurface in a higher dimensional space. This fact explains the origin of the term potential energy surface. To illustrate the concept of potential energy surfaces, we consider the following bimolecular reaction as an example. A molecule AB reacts with an atom C to form a molecule BC and release atom A. In this system, AB and BC are stable molecules. While we assume that the triatomic species ABC and the diatomic species AC do not form as stable compounds. In this reaction, atom C approaches molecule AB, leading to bond rearrangement and the formation of the new BC bond and the release of the atom A. This reaction can be viewed as a rearrangement within a three-atom system, and the key factor governing its dynamics is the potential energy of the system of atoms. So, the potential energy of a system of atoms depends on the relative positions of atoms in space. To fully describe the system of three atoms, we need three variables: the distance between the centers of atoms A and B, the distance between the centers of atoms B and C, and the angle theta between vectors BA and BC. Mathematically, the potential energy can be represented in a four-dimensional space, where the coordinates are the three spatial variables and the value of the potential energy. The potential energy as a function of these three variables, describing the arrangement of atoms, forms a hypersurface in this four-dimensional space, referred to as the potential energy surface. Since it is impractical to visualize a function in a four-dimensional space, we simplify the representation by introducing the following assumption. We assume that all three atoms A, B, and C lie on a straight line, meaning the angle theta remains fixed at 180 degrees. Although the assumption of a linear configuration may appear arbitrary, it is actually physically justified. In many chemical reactions, linear configurations correspond to lower energy pathways. In contrast, nonlinear arrangements often result in higher energy pathways and are less relevant for the analysis of the dominant reaction mechanism. This linear configuration significantly reduces the complexity of the system. With this assumption, the potential energy now depends only on the two interatomic distances. Now, after we have reduced the dimensional complexity, we can visualize the potential energy surface in a meaningful way. There are several common ways to do this. A three-dimensional surface plot is a direct representation of the potential energy as a function of the interatomic distances. A contour diagram is a two-dimensional projection where lines of constant energy are drawn, similar to topographic maps. Cross-sectional plots are slices through the potential energy surface along specific pathways. Each of these representations offers valuable insights into the properties of the potential energy surface. This 3D representation of the potential energy surface for our example reaction illustrates how the potential energy varies as a function of the interatomic distances RAB and RBC. The energy is plotted along the vertical axis, while the interatomic distances are on the horizontal axis. The arrows indicate the directions in which the interatomic distances increase. In the front part of the figure, we see a broad energy plateau, which represents the dissociated states, where atoms A, B, and C are all far apart and do not interact. When the interatomic distances are very small, the potential energy increases sharply, reflecting the repulsion between the pairs of atoms or between all three atoms. Two distinct energy minima corresponding to the stable diatomic molecules AB and BC are visible in the surface. We can see that the states surrounding such a minimum correspond to a stable chemical compound, because small deviations from the equilibrium configuration lead to an increase in the potential energy and forces the system to return to the equilibrium state. The surroundings of the minima are sometimes referred to as energy valleys of respective compounds. This figure shows a two-dimensional contour diagram visualizing the potential energy surface. It represents a projection of the three-dimensional potential energy surface onto two dimensions. It can be thought of as a view straight down onto the three-dimensional surface presented in the previous figure. Contour lines connect points of equal potential energy, similar to constant height lines used in topographic maps. To further analyze the potential energy surface, we can extract cross-sections along specific pathways. For example, figure D shows a cross-section of the potential energy surface along the line A, A'. It corresponds to a varying distance between the atoms B and C, while the distance between the atoms A and B is constant and very large. As there is effectively no interaction with the atom A, this cross-section simply corresponds to the already known potential energy curve for the interaction between atoms B and C. The minimum along the RBC coordinate corresponds to the equilibrium bond length of the diatomic molecule BC, and the depth of the potential is equal to its dissociation energy. Figure E shows a cross-section of the potential energy surface along the line BB', which results in a similar potential energy curve for atoms A and B in the absence of the interaction with C. Now, let's take a look again at the three-dimensional representation of the potential energy surface. We can see two distinct energy minima corresponding to the stable diatomic molecules AB and BC, and a dashed line connecting these two stable configurations. This line represents the lowest barrier pathway connecting these two stable configurations and is called reaction coordinate. In the context of reaction dynamics and potential energy surfaces of reactive chemical systems, the reaction coordinate is a very specific term. It should not be confused with either an arbitrary pathway on the potential energy surface or the extent of reaction psi. The reaction coordinate is defined as the pathway along which the system evolves with minimal energy expense, meaning that the least energy barrier must be overcome. Since reaction rates depend exponentially on the activation energy, as described by the Arrhenius equation, the pathway with the lowest energy barrier is the most probable. Let us return for a moment to our example reaction and consider the meaning of the reaction coordinate for it. The chemical reaction, the rearrangement of atoms in the reactants that leads to the formation of products, can be seen as a movement of the three-atom system on its potential energy surface. The actual trajectory of this movement depends on the total energy of the system, which is the sum of kinetic and potential contributions. Nevertheless, the path with the lowest energy barrier, the reaction coordinate, gives important insights into likely dynamics of the corresponding chemical reaction. It provides a useful first approximation of the path the system is most likely to follow. As such, it represents the reaction and determines the reaction mechanism. Consider now how the potential energy changes as atom C approaches the AB molecule. If the distance AB remains approximately constant during the approach, the system follows a path similar to that marked 1 in the figure. The potential energy initially increases as C moves closer, as indicated by a decreasing RBC, and begins to push into the molecule AB. This leads to compression of the AB bond as seen by the decreasing RAB. Then the potential energy peaks when all three atoms are in close proximity. After that, it drops sharply as atoms A detaches, seen as a rapid increase in RAB. The newly formed molecule BC relaxes by increasing its bond length towards the equilibrium value. This is indicated by a slight increase in RBC as the system approaches the bottom of the energy value for an isolated BC molecule. Alternatively, one could imagine a path like 2 in which the AB bond is already stretched as C approaches. This stretching can be seen as an increase in RAB, while RBC is still relatively large. This requires an upfront increase in the potential energy of the system. After that, atom A detaches and the newly formed molecule BC relaxes by further decreasing its bond length. However, both paths 1 and 2, although feasible if the molecules have sufficient initial kinetic energy, take the system through regions of relatively high potential energy. In contrast, path 3 represents the most favorable route. As atom C approaches, the AB bonds stretches slightly, allowing for a transition through the lowest energy barrier. the saddle point of the potential energy surface, marked here by a circle. This path involves the smallest increase in potential energy and corresponds to the reaction coordinate. It leads from the reactant valley, AB plus C, over the saddle point, the mountain pass, to the product valley, A plus BC, and represents the most probable pathway. As you have seen in the previous example, purely geometrically, the reaction coordinate, the pathway with the lowest energy barrier, must pass through the saddle point of the potential energy surface. This saddle point, or more specifically a critical region of configurations around the saddle point that the system must pass through to follow the lowest energy path from reactants to products, is referred to as the transition state of the corresponding reaction. All successful reaction trajectories must pass through this narrow region, making it the gateway between reactants and products. You can also see from this figure that the transition state is not a stable atomic configuration. The saddle point is a minimum of potential energy along the direction perpendicular to the reaction coordinate, but it is a maximum in the direction of the reaction coordinate. Following a small deviation from the saddle point along the direction of the reaction coordinate, the system finds itself in a state where it can lower its potential energy by moving towards either products or reactants. This figure shows a reaction coordinate diagram, which represents how the potential energy changes as the system progresses from reactants to products along the reaction coordinate. The maximum along the curve corresponds to the transition state. The transition state of a reaction is indicated by this nice symbol, which is called double dagger. Strictly speaking, while the transition state corresponds to a certain range of system configurations, the chemical species formed in the transition state is called the activated complex. Nevertheless, these two terms are often used interchangeably in this context. This figure also demonstrates very well that the activated complex is not a stable species, such as a reaction intermediate, but a mere transitional configuration of a system of atoms. We can now summarize the mechanism of the example reaction by explicitly including the activated complex. It proceeds as follows. The molecule AB and the atom C form the activated complex, which then breaks down into the atom A and the molecule BC. This example shows how the transition state plays a central role in determining the rate and outcome of a chemical reaction. Understanding the transition state is essential for analyzing and predicting the dynamics of a chemical reaction.